Hello, and welcome to my talk on the quantum Hall effect. I hope to convince you that the quantum Hall effect and the experiments that discovered them were arguably the most surprising and significant physics experiments of the last 50 years. I will describe these experiments and why their results were so unexpected and influential. And despite the fact that the quantum Hall effects reveal physics that is both deep and subtle, I will attempt to describe them in a manner that is accessible and maybe even enjoyable to a non-scientist. So let me first start with a quick overview of what the talk will be about. I'm going to start with some background definitions, which are going to be necessary for those without much of a physics background. Then I'm going to talk about the classical Hall effect, which was discovered in the 19th century already. Then I'll talk about what happened after quantum mechanics became on the scene and was discovered that the classical Hall effect was not the entire story. And then finally, we're going to come to the quantum Hall effects. First, the integral quantum Hall effect, which was discovered in 1980, and then the fractional quantum Hall effect, discovered in 1982. And finally, I'm going to talk about why the quantum Hall effects are so important. But before I can do anything, if this is going to be accessible to folks who maybe haven't studied physics since high school or never even took a physics class in high school, I need to define some terms so that you have some idea of what I'm talking about. So we're going to start with some terminology from electricity and magnetism. In fact, even before that, let's start very basically in physics. We need to talk about forces and energy. In physics, a force is an action, usually a push or a pull, that causes an object to change its speed, or in physics talk, its velocity, its shape, or its internal properties. Energy, which has all kinds of meanings in everyday life, in physics refers to the cumulative change of an object's speed, shape, or internal properties caused by the application of a force. Change of speed is called kinetic energy. Other changes are referred to as potential energy. We're also going to need the concept of a field. In physics, a field is a property of a physical phenomenon that has a value at every point in space and time. Something like temperature, for example, which has a value at every point in space and time. But we're going to be interested in electric and magnetic fields, and these are characterized by electric charge, which is a physical property of an object that causes the object to experience a force, to have its internal energy or its speed change when placed in specific types of field, which are called electric fields. And the amount of energy an object receives from an electric field divided by the electric charge of the object is called the voltage of the electric field. So basically, it's the amount of energy that some kind of a unit object or an object that has one quantity of electric charge will feel. The current between two points in space is the amount of electric charge that flows, that moves between those 2 points per unit of time. So that's just like the current in your household and your electronic appliances. It's the amount of electrons, the amount of charge that's flowing into your computer or your television per unit time that describes how much electrical energy is going into that device. And again, the current will depend on the shape of the device that's transmitting the energy, which is the wire typically in your house, meaning its shape, but also its material content, whether it's silver, whether it's copper, or some kind of a mineral alloy. And when one wants to specifically look at the intrinsic property of a piece of uh, material and how well it transfers electricity, and one looks at the current density, which is the amount of charge per unit time that flows through a unit area of some chosen cross section. The resistance of an object is the ratio of the voltage, meaning the force that's pushing the electrons, divided by the current, which is the number of electrons per second that is getting through the object. So it is telling you how much that object is resisting electrons going through it. Again, since that resistance will depend both on the shape of the object as well as what it's made of, one sometimes likes to separate those two if one is specifically interested in material properties of a material, and then look at the amount of resistance per unit volume or divided by a unit volume. And that ratio is called the resistivity of the object. So, for example, something like copper has a much lower resistivity than something like helium, because it's much easier to send electrons, to send a current through copper than through a block of wood, for example. We also need to talk about magnetic fields in addition to electric fields. They're also physical fields, which are related to but different from electric fields. And they have the interesting property that they cause a force to act on electric charges, but only electric charges that are moving. Electric fields exert forces on electric charges even if they're sitting still. So the magnetic field tells you per segment of unit of volume, how much of this magnetic energy is there. And if one wants to look at how much the total amount of magnetic field that's going through an area, that's called the magnetic flux. It's basically the sum of all the magnetic field that's going through a sphere or a circle or something of that nature. Okay, that's electricity and magnetism in 25 words or less. But we also need some terminology about measurements. And the reason is that the quantities, the things going to be measured in the quantum Hall effect tend to be rather different, of a very different scale than compared to quantities in our everyday life. So they get measured in ways that may be unfamiliar to you. So, for example, distances, which we're used to measuring in feet or yards or meters or kilometers, in this area of physics are measured in what are called nanometers, where 1 nanometer is 1 billionth of a meter. So we're going to be looking at things that are very, very small. And in particular, we're going to be looking at films that are very thin. And those distances or those thicknesses will be measured in nanometers. In addition, we're going to be interested in trying to get the effects of on one atom of something that we're going to be measuring on a block of material in a laboratory, which consists of a lot of atoms. And in fact, a very lot of atoms. And the number, roughly speaking, the number of atoms in a given piece of material is approximately what scientists call 10 to the 23rd, which means 1 followed by 23 zeros, which is written out there, and which you can see why the notation, which is called scientific notation of 10 to the 23rd, is more convenient than writing out 1 with 23 zeros after it. So we will use the number 10 to the 23rd at times to give you a sense of, say, if you have a cubic block of copper, and you want to know, well, how many atoms are there? Roughly speaking, give or take a factor of 10 or 100, it'll be 10 to the 23rd. Temperature is also a very different kind of quantity and quality than it is in everyday life, since we'll be looking at temperatures that are very close to what's called absolute zero. Absolute zero being the lowest possible temperature that is allowed by the laws of physics, which basically means temperature says is a way of describing in the physics sense, how many ways can a particle move? As the temperature gets higher, it can move in more directions and it can move faster and it can move in different ways. But when you get to absolute zero, the system's internal energy, the number of ways it can move internally, vibrate, rotate, reaches its minimum value. For example, you may have heard of liquid helium, which is what you get if you take gas helium and you cool it down so much that it becomes a liquid. That happens at what's called 4 degrees Kelvin, meaning 4 degrees centigrade above absolute zero. We're also going to need some terminology from atomic physics and from material science. First, I want to probably remind you that all materials, basically, except in very exotic situations, are made of atoms, which are made of three kinds of particles: electrons, protons, and neutrons. We're also at times going to need to talk about how many electrons or protons are again in a block of material of a specific dimensions. And then we'll talk about electron density, proton density, or neutron density, just the number of particles per unit volume. And then one other thing we're going to need to talk about is that in a material, there are all kinds of forces between the electrons and themselves, and between protons and themselves, and between electrons and protons. And in particular, the electron and proton force is attractive. They tend to pull them, the electrons tend to get pulled towards the protons. And when electrons are in a material, in a state, in a configuration where they've been restricted to be in a localized region, they are called in a localized state. On the other hand, electrons in some materials, and particularly the ones that conduct electricity well, like copper and silver, are able to move through the material relatively freely. Such electrons are said to be in an extended state. And so if one is trying to understand whether a property allows current to go through it or not, which will be very central to the quantum Hall effect, it'll be important to know whether the electrons are in a localized state or whether they're in extended states. In addition, as I mentioned, with all of these 10 to 23rd electrons, they're all generating electric forces, they're going to be a huge number of electron interactions, meaning forces where the electrons repel one another. This makes modeling electron movements in materials very complicated because everybody's affecting everybody else. As a result, when physicists try to make predictions or try to understand what's going on, they often model a system or pretend that a system doesn't have any electron interactions. In such a model, the electrons are called free electrons. Whether that model looks anything like what's really happening in real life or in the laboratory, that will remain to be seen for any specific example. But one can always pretend that there are no electron interactions, pretend that the electrons are free, see what happens, see if it agrees with experiments. Finally, before we can get started, we do need a few terms from quantum mechanics, from quantum physics. One of the most important ones is that quantum physics predicts that fundamental particles, such as electrons and protons, can only be in states with energies that have specific discrete values called energy levels. So for example, if we look at the picture on the left, and we have, these are the possible states on the horizontal axis that say any one of a group of electrons could have. And these might be, this is a made up example, but it characterizes systems to some extent. And these would say be the three energy levels that any of the electrons in this state could have. And it would be impossible. The fundamental thing here is that quantum mechanics tells us that for this system that's being described here, It's impossible for an electron to have an energy that's as indicated with the cursor right now. It either has this energy or it must have be able to have this energy. It is impossible to have something in between. If that sounds bizarre, it is bizarre. And it's but that's what quantum physics claims, and that's what has turned out to be what has been measured in the laboratory. This particular picture is sometimes rotated by 90 degrees, sort of turned on its side, and be useful to look at this way. And so instead of plotting, graphing the positions, the number of states in the horizontally and the energy of each of those states vertically, one just looks at the possible energies and notices that these three energies, it's possible to have a lot of states in this example, but at any other energy, it's impossible to have any state. And we also need to know one other thing. And the last thing, that last definition we're going to need here is that quantum physics also predicts that fundamental particles have one other very, well, actually many other very strange properties, but one particularly strange property, which is that if you have two particles that are in some sense the same, meaning they're both electrons, they both have the same spin, they're both located in the same place in physical space, then quantum mechanics says there are two kinds of particles. There's certain particles in which particles of any one type with the same spin, same location, et cetera, that you can pile as many of those on top of each other as you want. And there's no intrinsic reason why that can't happen. And there are such particles. The photon, the particle of light, is probably the most common example. Such particles are called bosons. That's kind of a funny name. It has nothing to do with the fact that they're considered to be bozos. It's just the name of a well-known physicist of the early 20th century, was a Mr. Bose. On the other hand, the only other type of fundamental particle is one where you can only put two particles of one type of the same type in the same energy state at the same time. Uh, Pretty much all the familiar particles that you may have heard of, electrons, protons, neutrons, they're all of this kind. They're called fermions after Enrico Fermi, and they also exist. But in particular, no one had ever discovered particles where you could only put three there or only put four there. Either you can put any number there or you can only put two. Okay, so we got some language. And now let's start talking about a little bit of physics. And let's go back to the 19th century. And in the 19th century, the big success was understanding electric and magnetic fields, which was done by Lorentz, but especially by Maxwell. And you may have heard of the Maxwell equations. And in particular, there's something that goes under the name of the Lorentz force law. It's quite important, was quite important in the 19th century and continues to be. And the basic thing that the Lorentz force law said was that if a particle moves in one direction, call it the x direction, whatever, and there's a magnetic field in another direction, a perpendicular direction, then the particle will feel a force in a third direction, causing it to move in a circle. I'll show you a picture in just a moment, maybe help a little bit. And it'll also get, in that situation, and this is kind of important, it will get energy from this magnetic field, which will be what's called directly proportional to the magnetic field. And all that means is that if you have some way of doubling the magnetic field, for example, you will double the kinetic energy that goes to the particle. If you cut the magnetic field in half, you will decrease the kinetic energy going to the particle by a factor of two. So pictorially, this is what I just said is what's illustrated on the picture on the left. So you have a particle illustrated by this green dot. This is obviously all very, very conceptual. but it does illustrate what's going on. And if it's going, say, in the direction indicated by this blue arrow, and there's a magnetic field indicated by the direction of this red arrow, then there'll be a force that is perpendicular both to the speed, to the velocity of the electron, and also perpendicular to the magnetic field. So in this case, it'll go inward or go to the left, and that'll push the particle around this circle. So for example, when the particle gets here, it's moving in this direction. The magnetic field is still this way, so it'll start to feel a force pushing it back into the paper and continuing going around the circle. In a more realistic, this would be a case if you somehow had an isolated electron. In a more realistic case, you would say have a current, which is which is basically a collection of 10 to the 23rd, roughly, electrons flowing along a piece of wire, say in this direction. If you then had a magnetic field, which would be caused, say, by two magnets, which could be as simple as refrigerator magnets or as complex as magnets from a magnetic resonance machine going in this direction, then there will be a force on that piece of wire pushing it down. So this Lorentz force then led scientists shortly thereafter, including Mr. Hall, to think of an experimental configuration where you could actually measure this kind of thing. And this led to what was called the Hall effect, which is basically a somewhat just more complicated version of what I just showed. You have a current flowing through this blue thing, which is being pushed by the voltage of this battery or voltage source. You have a magnetic field going up. And if you have those two things, then the prediction is there will be a force on the electron pushing them in a perpendicular direction here along the red direction, which you'll be able to measure with a voltmeter. And this is called the Hall effect voltage. And it was measured already in the 19th century. And the measurements agreed quite well with what the theory of Mr. Maxwell and Mr. Lorentz had predicted. And that was the status at the turn of the 20th century. And in particular, the Lorentz force predicted two things. One thing was that in the direction that the electrons are moving here, the magnetic field shouldn't make any difference at all. So the longitudinal resistivity, meaning the resistance in this direction, shouldn't change as you turn up the magnetic field. On the other hand, as Mr. Hall predicted, the resistance in the perpendicular direction should change as you increase the magnetic field in a linear way. So that's saying this in words here. The longitudinal resistance, which is the ratio of the voltage to the current in the direction of the electric field, should not change. But the transverse resistivity, meaning the ratio of the voltage in the transverse direction to the current, should increase linearly. And this little equation, that's all it's saying is that if you can, B is often the symbol for magnetic field for reasons I have no idea, and rho is often the symbol for resistivity. And it just says that there is some fundamental constant, which in this case is the number of electrons times the electric charge, that relates one to the other. So that was the prediction. And this was the graph that was measured by Mr. Hall and his immediate successors. And what it shows here on it showed a system where you could slowly and systematically increase the magnetic field. And that's being described in the horizontal direction, in the X direction. And it's important to note that the magnetic fields here were very small. They were what are called less than 1 Tesla, where Tesla has nothing to do with the automobile. It's just the standard unit of magnetism. And just to give you a sense of what 1 Tesla is, if your typical refrigerator magnet is approximately 1 millitesla, which is 1/1000th of a Tesla. So these were all very small fields, magnetic fields. And the predictions, again, from Mr. Hall. One was that in the direction of the current moving, the magnetic field shouldn't make a difference, and that seemed more or less to be the case. And in the direction, the perpendicular direction, Mr. Hall's direction, the effect should linearly increase with the magnetic field, and indeed, that's what you see. So again, so one sees that the experiment confirmed the predictions of the class, what's now called the classical Hall effect, which back then was the only Hall effect. And this was pretty much the status of physics, and it was, till about the early 20th century when quantum mechanics was discovered and kind of turned physics on its head. And I'm not going to go into talk about much about quantum mechanics, but I do want to say a few words about how quantum mechanics affected the class, was predicted to affect the classical Hall effect. In a lot of ways, quantum physics left the classical Lorentz force and Hall effect unchanged. But there were two significant changes. One was that the allowed particle energies, the amount of energy that any given electron could have, were suddenly quantized. In the jargon, they were quantized to specific levels, which in the jargon were called Landau levels. And in addition, that this is, as I mentioned earlier, the Pauli exclusion principle was the name of this phenomenon that two electrons can't be in the same state at the same time, which implied that even at very, very low temperatures, something strange was going to happen because would have expected that the lowest possible energy in classical physics, the lowest possible energy for a system would be that all of the particles would be in the lowest possible energy state. But Pauli said that's not possible in quantum mechanics. It's only possible that two electrons are at the very lowest state, two at the next lowest state, and so on down the line. And that was going to have some effect if you looked at low temperatures, uh, if you looked at experiments at low temperatures. So the result of applying so the result of applying quantum mechanics to the classical Hall effect was first derived by two gentlemen by the name of Shubnikov and de Haas in the 1930s. And they predicted that because of these new effects at low temperatures, which meant less than 20 degrees Kelvin, so very, very cold, we're talking in Fahrenheit, 400, more than 400 degrees below zero, and at very high magnetic fields, meaning higher than half a Tesla. And give a sense of what that is. If any of you have been around an MRI system, that's what, MRI systems are roughly in that general ballpark of magnetic field. So if you've got such super low energies and super high magnetic fields, then the quantum mechanics predicted that the Hall resistivity should be the same as predicted by the classical Hall effect, while the longitudinal resistivity should oscillate, should go up and down as a function of magnetic field. That was the prediction of quantum mechanics. And when the experiments were done in the early 20th century, in the 1930s, lo and behold, that's exactly what happened. As you can see, if you look at this part all the way at the end, you see this is what Hall and his peers noticed, which was that the longitudinal resistivity was constant, was independent of the magnetic field, and that the Hall resistivity was proportional to the magnetic field. But once you started to go up to 1 or 2 Tesla, the um, the magnetic field of the horizontal, the longitudinal magnetic field started oscillating quite wildly, whereas the longitudinal one stayed more or less the way it was before. So that was the status of the Hall effect from the 1930s until 1980. And around 1980, certain things had changed from the world of technology. Specifically, it now became possible to consider doing the Hall effect at under even more extreme conditions than had been done before. In particular, it was possible to go to even lower temperatures than 20 degrees Kelvin. In particular, one could go to 4 degrees Kelvin by using liquid helium. It was possible to go to even higher magnetic fields, up to 5 Tesla. This required using superconductors and in very elaborate and sophisticated configurations. And it also was possible to go to even thinner um, uh, experimental configurations, which were even closer to be in 2 dimensions, which is where the Hall effect takes place. I actually neglected to mention that, but the Hall effect, in order to see it, you had to have relatively thin pieces of material. But they they were not that thin in the late 19th century, whereas and even the early 20th century. But by 1980, it was possible to create systems that were 20 nanometers thick. This required semiconductor fabrication of the kind that's done in Silicon Valley, or later the use of a very interesting material called graphene, neither of which am I going to be talking about. Having said all that, the assumption was, or the belief was, and I think in the overwhelming majority of the physics and scientific community, that what one had observed from the Hall effect would remain pretty much the same, just extend the graph that we saw from Shubnikov, would it continue to look as it uh, had before. This is just a very quick picture that I'm not going to particularly explain, but just gives a very rough schematic idea of how one creates these very thin films in places in semiconductor fabrication laboratories, where when has to put on do lithography and make thin films of insulators and currents and semiconductors, and then one winds up getting a very, very thin order of a few nanometers thick um, sample on which one can do these experiments. These were the results of the 1980 experiment. To say the least, they were completely unexpected. If you look here at this part of the graph, this was down below 2 Tesla, and it was basically what had been observed in the 1930s until 1980, which was that the longitudinal resistivity went in a straight line, and the I'm sorry, the Hall resistivity went in a straight line, and the longitudinal resistivity oscillated. But beyond about 2 Tesla, things got totally different. A few things you'll notice. The one thing is that at certain places, the the Hall resistivity flattens out. Also, these oscillations completely change. In particular, one discovers that the quantum Hall effect resistivity has plateaus, as I just said, at specific ratios of the magnetic field to the electron density. And that's, again, I'm just showing the same thing here. And the other thing that turned up was at those plateaus, the longitudinal resistivity went to zero. As you see, at those plateaus, the longitudinal resistivity, instead of continuing to oscillate, suddenly goes to zero. Both of these results were extremely unexpected. In fact, um, oh, I should say there one more thing, yet one other thing that was dramatic was at the plateaus, the Hall resistivity itself was quantized, meaning which is just physics jargon to say that the resistivity was some fundamental constant of nature times 1 over some integer, 1, 2, 3, 4. It was not anything in between. So for example, here at this level, the resistivity is that formula I just showed where the number nu is 8. Here it is 6. Here it's 4. Here it's 3. But there's never a plateau at any place, which is this one here probably is 5. Um, where there's no place in between where there's a plateau where the flux, which is what this new is measuring, the magnetic flux that I mentioned, is anything except a precise integer times this one fundamental constant of nature. Moreover, it turned out that even when they started that these precise numbers, this was a precisely an integer, like two or three, it didn't seem to matter if there was a certain amount of impurity or defects in the material. It was something that you didn't have to have a super pure piece of material to observe this. It was independent of the impurities of the material. Needless to say, or it is certainly true, all these results were totally unexpected. As a result of that, Klaus von Klitzing, who was the one who performed and published these first experiments, won the 1985 Physics Nobel Prize. It's interesting to note that several scientists, including some quite reputable ones, said later that they now realized that they had seen the quantum Hall effect in some of their low temperature experiments, but it was so unexpected and so um, unbelievable that they thought that they had made that there had been some sloppiness in their experiments, and they didn't believe it. And even von Klitzing said that he had observed the effect approximately a year before he published his results because he thought his results were were a mistake. And I should also mention that one other person received a Nobel Prize for the quantum Hall effect. His name is Andre Geim, and he received the Nobel Prize for doing, among other things, creating the quantum Hall effect in graphene. And I always like to mention Mr. Geim because I have a lot of respect for him. He is an interesting character because, among other things, in particular, he's the only person who has won both the Nobel Prize and the Ig Nobel Prize, which is given each year to the scientist who's come up with absolutely the craziest experiment that you can think of. In Mr. Geim's case, it was for levitating a frog with a magnetic field. Okay, so how did this happen? What was going on that no physicists, no scientists had thought of or had ignored, and as a result of which they were so surprised by the integer quantum Hall effect? It turns out there were two phenomena that were very important, and that although everybody realized that they existed, no one realized just how important they were. One of them was edge effects, was what happens on the border of this very thin sample, and the other was the effects of disorder. What are the effects of material imperfections? So let's talk for a moment about edge effects. And in the presence of a magnetic field perpendicular to a two-dimensional circle. So here we have a sample. This is obviously very schematic, but so the magnetic field is coming out of the screen, and the dimension going into the screen is very, very thin. This is nanometers, and these are the electrons, and the particle orbits that are predicted by quantum mechanics and are observed in the bulk of the sample are these circles where basically the electrons go around in circles, and so there's no current, meaning to say there's no way for electrons to get from one side of the material to the other and thereby generate a voltage that can be measured. However, near the sample edges, the orbits cannot be completed due to collisions with the boundary. A picture might make this a little bit easier. Um, I'll show you the picture momentarily. But although there's zero current within the bulk of the material, there can be currents and will be currents on the edges. So this is the picture. Again, in the bulk of the material, this is the way it looks. This is the way it looks like in the bulk of the material. But on the edges, when the electrons attempt to go in a circle, they can't because they reach the end of the material. And so it's along the edges of the material is where the currents that generate the quantum Hall effect come from. And this was something that was not appreciated how important that was. The second thing that was very important, and it was not really appreciated, was the importance of disorder, meaning to say imperfections in the material, and that these would change the possible orbits, the possible paths that the electrons can take in the material. So a picture again might help a little bit, but I'll show you the picture of the electron motions momentarily. But before that, again, I remind you that in a pure material, quantum mechanics predicted that if these are the possible energies, then only at certain energies could there be states, could there be electrons actually having those energies. But it turns out that if there's disorder in the material, this was true for a pure material. Quantum mechanics was derived, the original theories were derived from making up the assumption that the material was pure copper or pure silver. However, in real materials, there are imperfections. They're traces of other materials, traces of other minerals inside. And when that happens, quantum mechanics will show that actually there are other energies that are allowed, and not just the ones that were those from the pure material. But what was even more surprising, with what was discovered when one did the physics much more carefully, was that the electrons that had exactly the energy that had been predicted for the pure material, they were in what were called extended states. I'll show you a picture in a moment. Whereas the ones from that didn't have exactly the right energy, they were in localized states. So again, so this is the picture, which is that if your magnetic field changed slightly, so that the energy right on the nose changed slightly, then you would have some states that were off, that had the wrong quantum Hall voltage, but those states would be localized and they wouldn't be able to create a current. It was only the electrons that had precisely the velocity and precisely the energy of the quantum Hall effect were able to form extended states and thereby could create currents that could be measured. This was this won't be obvious to you. It's not obvious to me. And it wasn't obvious. I mean, nobody thought of that until the experiment was there. And even after the experiment was done, it took some very clever physicists a while to understand why this phenomenon was happening. So this was the status as of around 1981, 82, when finally, through studying edge effects and disorder, the integral quantum Hall effect was understood. And it was assumed that that was the end of the story and that the picture would just continue the way it had. If it had been measured by Mr. von Klitzing, even if one went to even lower temperatures and even thinner materials and even higher magnetic fields. So in particular, by 1982, it was possible to lower temperatures down to 1 degree Kelvin, which required what was called vacuum pumping of liquid helium. It was possible to go to even to 15 Tesla, which required very powerful superconductors. And it was possible to create even thinner two-dimensional systems, less than 10 nanometer thickness, which required even improved semiconductor fabrication techniques. And once again, I think it's safe to say maybe there wasn't quite as much surprise, but that the physics community in general thought that what had been seen in 1980 by Mr. von Klitzing would continue to be seen as one went to these more extreme situations. And we recall this is what was seen in the integral quantum Hall effect. This is just the same picture that I showed a few minutes ago. But and this was going, as you'll see, up to 8 Tesla. So the question is, well, what happens when you went beyond 8 Tesla? So here's 8 Tesla, and as you see, once again, once you went to a different region, all different hell breaks loose. Things look totally different. Part of the difference here is the pictures and drawn to a somewhat different scale, but the essence of it is, for example, if you look at the quantum Hall voltage, you have these plateaus that we had seen at 3 and 2 and 1 at integral levels, but suddenly they're finding plateaus at 2/3, and there's a plateau at 3/5 and at 8/5. They're smaller plateaus, but they're there. Here's one at 2/5. Plateau meaning a place where where suddenly or over a period of fairly significant change in magnetic field, the Hall resistivity does not change. Moreover, at those various places, once again, the longitudinal resistivity goes to zero, even at 4/5 or at 2/5, and not just at integral values these are again the values of the flux of the total magnetic field. Again, these results were totally unexpected. So to summarize what I just said, in the integer quantum Hall effect, again, as in the integer quantum Hall effect, also in the fractional quantum Hall effect, the longitudinal resistivity goes to zero, and the Hall resistivity has a constant value related to that. It's a multiple of the flux, and at various plateaus. And again, the results are largely unaffected by defects or impurities in the material. However, the big change is that now at these very high magnetic fields and low temperatures, that flux is not only takes on not only integer values, but certain fractions like 1/3 and 2/3 and 2/5 and 1/2. So this was almost as unexpected as the original Hall effect, and it again resulted in a Nobel Prize. Um, Stormer and Tsui, the two people on the side in this photograph, received the 1998 Physics Nobel for discovering the fractional quantum Hall effect. And Mr. Laughlin, the gentleman in the middle, shared the Nobel Prize because he was the first one in it to come up with a very clever way of seeing how, if you really looked at the quantum physics inside materials at ultra low temperatures and ultra high magnetic fields, it is not that unbelievable that you would have these effects. So what did Mr. Laughlin basically tell the world? And this is, I'm going to be giving a very, very simplified version. But basically, what he found observed was that whereas the analysis of the integral quantum Hall effect proved, in quotation marks, that magnetic flux had to be quantized to integers, 1, 2, 3, or 4, he observed, well, that's not the case. Tsui and Sormer did the experiment, and that's not the answer they got. And that meant that at least one of the assumptions underlying the analysis of the integral quantum Hall effect was no longer correct at the lower temperatures and higher magnetic fields used at the fractional quantum Hall effect. So scientists had been assuming something, and they had made an assumption that was wrong. And the key was that at the temperatures, magnetic fields, and sample thicknesses that were in this extreme situation, the interactions between electrons could no longer be ignored. That in the early analysis, the integral quantum Hall effect, one was assuming that the electrons were all free electrons and were not affected by the other 10 to the 23rd electrons there. And that actually succeeded in explaining the integral quantum Hall effect very well. But as when you got to super low temperatures, that assumption was no longer true. So let's step back for a moment and look at that assumption. How do you model interactions among 10 to the 23rd particles? You have all these particles, and every one of them is repelling every other one of them. It seems hopelessly complicated. And indeed, one approach, the simplest approach is just to ignore it. And that's what's often done, and that's to assume you have free particles, or in the case of a real material, that means free electrons. But if that doesn't work, a sort of less grandiose or a less modest approximation, or a more modest approximation perhaps, is to postulate, which basically in physics speaks just means to guess, that the effects on any one electron by all the other electrons could be approximated by replacing all those other electrons by one or a few imaginary so-called composite particles and say, well, let's pretend that all these other electrons have the effect of one other strange particle that would be doing the same thing. Is it possible to consistently imagine such a collection, small collection of particles that one can handle using the mathematics of physics, so you can make a prediction and see whether you can find such a model which agrees with experiments? Such composite particles would only exist within the material. They don't really exist outside. They're a mathematical construct that is used to see if you can predict an answer in a situation where it's too complicated to actually do any calculations for the real situation. And this is actually not such an unusual, this approach has been used for many years in the physics of what's called condensed matter, where you have 10 to the 23rd, solids and liquids, where you have all these different particles interacting with each other all the time. Examples of such models in physics that some of you may have heard of include holes and phonons in crystal physics and Cooper pairs in the theory of conductivity. Again, none of these are real objects in the sense that they have ever been observed or could ever be observed outside of the material, but they're extremely useful theoretical constructs for building a model that can be calculated and actually winds up making predictions that are verified in the laboratory. And similarly, what was discovered was that one could hypothesize um, a new kind of composite particle, imaginary hypothesized particle, that if you believed it was there, if you pretended it was there, you would get a prediction that matched what was then the fractional quantum Hall effect. And these particles were given a name. They were called anyons. They still are called anyons, and they're very strange. They're much stranger even than holes or Cooper pairs, if some of you are familiar with them. And the strangeness, the intrinsic strangeness of the anyons is linked to the fact that they're not localized the way an electron is localized. I mean, an electron has a wave function, for those of you who know a little physics, but it's still mainly localized in space. Whereas the anyons, their properties depend in a very intrinsic way on the entire system, on the entire block of material, or thin film of material, perhaps better said. The anyons depend on the global, or in the mathematical terms, the topological form of the material. Some of the strange properties of anyons that were specifically strange to physicists, as I mentioned, one of the fundamental tenets of quantum mechanics is that all particles could only be bosons and fermions, or fermions. And in a sense, that's still correct because um, anion quantum mechanics talks about real particles that you can actually observe by, flying around through an accelerator in a laboratory. But these hypothetical theoretical particles, like anyons, which only exist in a mathematical construct to describe condensed matter, it turns out that they have quantum states that are neither bosons nor fermions. More than one anion can occupy a quantum state, so they're not fermions, or if they have spin, no more than two. Yet the number of particles that can occupy a quantum state may be limited, so they're not bosons. Moreover, these anion states are robust. Even though they're mathematical constructs, they're not affected by perturbations or material impurities. The same model that works for a pure system, of the same model of anions, works for systems with material impurities. But what gets even stranger is that anions have electric charges that are fractions of an electric charge of the electric charge of an electron. And some of you may have heard of quarks, which are also hypothetical mathematical particles that have never been observed in the outside of a sort of a physically theoretical structure that have electrical charges of one third or two thirds. Um, but anions have an even wider array of electrical charges. And in fact, those plateaus that you saw earlier with, for example, where nu equals 2/5 or 2/3, it's because you have an anion or you have anions with electrical charge of 2/5 or anions with electrical charge of 2/3, which are in some sense causing, meaning to say that the model with the anions having an electric charge of 2/5 reproduces the actual experimentally observed phenomenon at the plateau of 2/5. And last but not least, anion states are only allowed by the laws of quantum mechanics in two dimensions. Um, or perhaps better said, in almost two dimensions. I mean, we live in a three-dimensional world. That hasn't changed. But it turns out that quantum mechanics says that if you can make a thin film thin enough, it's close enough to being two dimensions. And suddenly, anions can exist. And whereas in our usual three-dimensional world, there just aren't many anions. So they're extremely strange, but yet at the same time, if you assume they exist, or at least exist inside the material, you have yourself a prediction which matches which has been measured in the laboratory to extreme precision. So in the last few minutes, I would like to say a few words about just why the quantum Hall effect, in my opinion, is so important in physics. The first reason, and this was especially true of the integral quantum Hall effect, unlike most experimental physics discoveries, such as finding the positron or finding the Higgs boson, which you may have heard of, they were very important experiments, but basically they just confirmed what theoretical physicists had been saying for years. On the other hand, the quantum Hall effect, as discovered by von Klitzing, demonstrated a phenomenon which was totally unexpected. I mean, unexpected so much that people didn't believe it for a few years. The second thing that I haven't really talked about at all, but has been very important from a practical standpoint, is that because those measurements of the Hall resistivity are integers, or later fractional multiples, but importantly that they were integer multiples of a fundamental constant. It meant you could make, and that they were independent of any kind of material impurities. It meant you could make extremely precise measurements of things like resistivity, conductivity, and it has led to what it was now measurements that are accurate to within one part in a billion, which have allowed the definition of a new practical standard for electrical resistance. The fractional quantum Hall effect, on the other hand, maybe wasn't quite as, it was pretty unexpected, maybe it wasn't quite as unexpected as the integral quantum Hall effect, but it had probably even more profound impact on the world of physics and the world of science, because it provided the first and still most convincing experimental evidence of the world of two-dimensional quantum physics, of the world of anions, and the world where topology, which is which I'm not going to be able to get into, but is the mathematical world where donuts and coffee cups are the same thing, and you can, that's very bizarre mathematical world has a relevance to the real physics, has relevance to experiments that can be done. And finally, and perhaps most speculatively, the stability of anions make them the most promising candidate for use in the still unproven world of quantum computing. And, you may have heard of quantum computing. It gets a lot of hype. Um, and it may or may not ever be successful. But if it has a chance of working at all, chances are it'll be because it'll be by using the physics that is described by anyons and that was first discovered in the fractional quantum Hall effect. So that's pretty much it, what I have to say about the quantum Hall effect. Um, I hope you found it interesting. And and if you have questions, feel free to put them in the chat, and I'll be glad to take a look at them.